Hey guys, so today let's talk about resonance structures and formal charges. So let's start off with resonance structures. So let's look at sulfur dioxide for a sec. So by the instructions we talked about in the last video, we would make sulfur dioxide look something like this, right? Sulfur, double bond to an oxygen, single bond, pair, and like that. But wait a second. But if there's a double bond on the left side, is it the same thing if we have a double bond on the right side? Actually, yes. The two are actually the same molecule. But why do they have the same different structures? Well, we'll talk about that a bit later. For now, let's look at odd electron compounds. An odd electron compound is a compound that doesn't actually have paired electrons. So it always has at least one unpaired electron. Actually, one. So for nitrogen dioxide, for instance, it will look something like this. You may have noticed this little unpaired electron right here. So these are called free radicals. A radical is basically a chemical molecule, except it has an unpaired electron which it can bond onto. Another is the hydroxy radical, a common radical found in alcohols. Now there's another property of radicals, so-called dimerization. It's when two free radicals combine with each other to form something called a dimer, which is basically a pair of molecules acting like one. For nitrogen dioxide, it would convert to dinitrogen tetroxide. Honestly though, for nitrogen dioxide, it's really just equilibrium based. If it's hotter, then it will turn to NO2, and if it's colder, then it will become dinitrogen tetroxide. Now, let's look at formal charge. So how do you calculate formal charge on an atom? Well, first you count all of the electrons that are not used for bonding in each atom. Not used for bonding. And then number 2, multiply all the bonding electrons by 1/2. So in other words, divide all the bonding electrons numbers by 2. Step 3, add these two results. And then 4, subtract step 3, so this, from the valence electrons in the atom. And then number 5, try to minimize the formal charge on the atom. That makes the more reasonable structure. So here I have the structure of the phosphate ion. So let's use the instructions from earlier. Well, let's see, we have, how many electrons do we have not bonding in phosphorus? Well, we don't have any. So that would be 0 for step 1. Step 2, multiply the bonding electrons by 1/2. Well, we have 1, 2, 3, 4 bonding pairs, which means 8 electrons. Divided by 2, that would be 4. Add them up, that's 4. Subtract 4 from the valence electrons of phosphorus, which is 5, you get 1. This is positive 1. So the formal charge of phosphorus is positive 1. Let's use the same equations to calculate the formal charge on all the oxygens. So let's count the electrons not used for the bonding in each oxygen. 1, 2, 3, 4, 5, 6. 6 plus, how many electrons are used for bonding? Well, 2 divided by 2, that would be 1. That would equal 7. 6 minus 7 equals -1. So the formal charge on oxygen will be -1. Now all formal charges in the atom or molecule or ion will always add up to the overall charge. So let's do that. Phosphorus is 1, -1 because 1 oxygen, 2 oxygen, 3 oxygens, 4 oxygens, we get -3, right? Because these guys cancel. -1 times 3 is -3. 3 minus charge on phosphorus. Therefore, our calculations are correct. But, do you think there's any other way we can minimize these formal charges? Actually, yes. Let's look at this. So in this structure, this is an alternate way to describe the phosphate ion. So the thing that's different here is that now the oxygen here has a double bond. So let's do some formal charge math again. 0 non-bonding electrons on phosphorus, plus 1, 2, 3, 4, 5 bonding pairs. So 5 minus 5, obviously that would be 0. So the phosphorus' formal charge here is 0. We're getting on the right track here because ideally we want to minimize the formal charge. So let's look at all of the oxygens with a single bond now. So we have 6 non-bonding electrons, 1 bonding pair, 7, 6 minus 7, -1. So all of the oxygens with the single bond have formal charge of -1. And the oxygen for the double bond would be, well, let's see, 4 non-bonding electrons, 2 bonding pairs, 6 minus 6, 0. So which do you think is more reasonable? This structure or this structure? Well, if we count all of the atoms that have formal charges, you'll see that structure number 1 has 5 atoms that have formal charge, while this structure only has 3 atoms that have formal charge. So all we have to do is look for all of the structures that are possible and then find the most reasonable one by picking the one that has the least formal charge. Whenever we think of the most reasonable structure, we always try to look for the structure that has the least formal charge. Let's look at another example. This one is Nitroxyl Chloride. Nitroxyl Chloride appears in many different forms. So I have 4 of them. Now let's look at the formal charges for each of them. So you may have seen the labels I put here. So look here. Here's the formal charge. Now if you look here, you'll see that structure number 1 for nitroxyl chloride, which is this one, has no formal charge for each and every atom, while all of these other ones do have at least 1 formal charge. So that means that structure number 1 is the most reasonable structure because you can tell that it lacks any formal charge. So this is where resonance structures kick in. Now for the last one, resonance structures were pretty easy since the formal charges were, well, all different. But here, all the formal charges are the same. Look at the nitrate ion here. This nitrate has a double bond on this oxygen. This one has a double bond on this oxygen. And this one has a double bond on this one. What's the major difference between all of these nitrate structures? Now the only major difference is where the double bond is located. So which oxygen has a double bond? Well, we can't actually write all of this on our answer sheet. So we draw it like this. We draw N and then line dot 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 O, line dot 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 O, line dot 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 O, like that. So you just take the average of all of the bonds. So there's 3 oxygens, right? And 4 bonds. 4 divided by 3, that's 4/3. So we just assume that each nitrogen to oxygen bond is 4/3 bond. Now when we're talking about resonance structures, the benzene ring, also known as the aromatic ring, is worth mentioning. Look at the benzene structure here. We have 2 structures. But what's the major difference? Well, again, it's just where all the double bonds are. This one has one between these 2. Let's call them 1, 2, 3, 4, 5, and 6 just for simplicity. Model number 1 has a double bond between 1 and 2, 3 and 4, and 5 and 6. But model number 2 has double bonds between 2 and 3, 4 and 5, and 6 and 1. So it's just about where the double bond really is. So sometimes we just draw it like this, given the resonance structures. Because think about it, and you'll get that each carbon-carbon bond is technically 1.5 bond. So that was all about resonance structures and formal charges. Thanks for watching, and see you in our next AP Chemistry videos. Bye!